Today we're going to discuss about Bayesian theorem and probability. First, what is probability and how likely something is to happen? Many events can be predicted with total certainty. The best way we can say is how is likely is to happen, using the idea of probability. After discussing the concepts of probability, we are now going to discuss the one of its theorem, which is Bayesian theorem or Bayesian probability. Bayesian probability is an interpretation of the concept of probability, in which frequency or propensity of some phenomenon, probability is interpreted as reasonable expectation, representing a state of knowledge or as quantification of a personal belief.
In probability theory and statistics, Bayes' theorem, also called as Bayes' law or Bayes' rule, describes the probability of an event based on prior knowledge of conditions that might be related to the event. Bayes' theorem is named after Reverend Thomas Bayes, 1701 to 1761, who first provided an equation that allows new evidence to update his beliefs in his essay, An Essay Toward Solving Problem in a Doctrine of Changes in 1763. Here is the equation. But when Bayes dies, he didn't have the chance to tell anyone what he is up to. Soon after his philosopher body, Richard Price discovers Bayes' notebook and uses it to revolutionize insurance business when they needed probability to review of buy. In 1812, a Frenchman named Pierre-Simon Laplace developed Bayes' theorem to more suitable theory known as conditional probability, and it was published in his book Theorie Analytique des Probabilités. Another is Alan Turing, a computer scientist who uses Bayesian probability to crack secret transmissions. There is also Sir Harold Jeffreys that put Bayes' algorithm and Laplace formulation on axiomatic basis. He wrote, Bayes' theorem is to theory of probability what the Pythagorean theorem is to geometry.
For example, will it be sunny? Oh my god! Or will it be rainy today? Another example is tossing a coin. There is a 50-50 chance to get heads or tails.
When tossing a coin, there are two possible outcomes, getting the head or getting the tails. But in reality, what are the chances of getting either heads or tails? In general, probability of an event happening is equals to the number of ways it can happen all over the total number of its outcomes. In our example, we can say that the number of ways it can happen is 1 because there are only one way that the head or the tails can show up. And there are two possible outcomes, which is getting the heads and the tails. So when tossing a coin, getting heads or tails have a probability of showing 1/2. Another example is throwing a dice. When a single die is thrown, there are 6 possible outcomes. Let's say, what are the chances of rolling 4 in a dice? The number of ways it can happen is equals to 1 because there is only one face of 4 on it, and the total number of outcomes is equals to 6. So the probability of getting the 4 in a dice is equals to 1/6. To justify what a probability is, I'll give you another example of probability. The probability that a blue marble gets picked when there are 5 marbles in bag, 4 are blue and 1 is red. So the number of ways it can happen is 4 because there are 4 blue marbles in the bag, and the total number of outcomes is equals to 5 because there are 5 marbles in total, including the red one. So the probability of getting or picking the blue marble is 4 over 5 or 0.8 chance. Probability line. We can also show probability on a probability line. The probability of an event occurring is somehow between impossible and certain. This probability of an event will not be less than 0 because 0 is impossible, and the probability of an event will not be more than 1. This is because 1 is a certain that something will happen. So the probability does not tell us exactly what will happen. It is just a guide.
Say the probability of getting dengue fever while visiting Bermuda for a week is 1 in 10,000, or 0.01%. I'm totally making this up. You go to Bermuda, come home, and to be safe, take a test that is 99.9% accurate in detecting the virus. Your test comes back positive. You start to freak out, saying goodbye to loved ones, writing out your will, and are about to adopt a new religion when you take a second Bayesian look at the results. Remember, for every one person with the virus, there are 9,999 people without it, which means that even a robot programmed to always spit out a negative test result, regardless of who's taking the test, would still guess correctly 99.99% of the time. Being accurate 99.9% of the time, then, isn't really that impressive. What you really need to figure out is how accurate that test is when it spits out a positive result. When this one person with the virus takes a test, chances are 99.9% that it'll be accurate. Out of the 9,999 people without the virus taking the test, 99.9% of them will get an accurate test result, which translates to 9,989 people. That means that the remaining 10 people will be inaccurately diagnosed, testing positive for dengue fever when they don't actually have it. So, out of the 11 people testing positive for the dengue virus, only one of them actually has it. Meaning, the chances your positive test result is right is only 1 in 11, or 9%, not 99.9%. Now swap dengue fever with HIV, and you're looking at an actual, real-life example people have found themselves in. Conditional probability works pretty well, and can literally save your life. But the big thinkers of the day aren't impressed with the phrase works pretty well. They're all about frequentist probability, a more popular approach that claims that the only way you can really know the odds is to have lots of hard, objective data that backs you up. Let's say you flip a coin once and it lands heads. Based on that, you might assume it's always going to land heads, but that'd be pretty stupid. We all know that the more times you flip a coin, the closer it's going to get to landing heads just half the time. That's the whole point of frequentist probability. Flip that coin enough times and you'll have good enough data to take on Vegas. To those guys, Bayesian probability is like shooting an arrow half blindfolded and hoping you hit the target. But most of the time, that's exactly where you find yourself, needing an answer without having much to go on. That's why World War II hero Alan Turing, that nerdy British guy who dreamed of computers way before Steve Jobs did, used Bayesian probability to crack top-secret transmissions, some of them sent from Der Fuhrer himself. Despite this, the frequentists still think Bayesians are lame, and the rivalry continues deep into the 20th century. But then, the 1980s. People had been trying to make artificial intelligence a reality since the 60s, programming computers with basic logic like, if X is true, then Y happens. That approach works fine as long as X is always true, but as you can guess, there are too many unknown variables in the real world to bring C-3PO to life. But then, in 1988, Judea Pearl jumpstarts AI with a new approach based on, you guessed it, Bayes' theory. So that's why in 2011, when a computer called Watson beat a couple of humans answering questions on Jeopardy, it was Thomas Bayes running around inside Watson's brain going, if this is true, then that might be true. And if that other thing is true, then I'm gonna buzz in with, what is Chicago, Alex? 250 years after he flipped his last coin, it turns out Bayes' odds were pretty damn good.
Thank you for watching! Thank you! Yeah.